Welcome to this Environmental Resilience Sustainability Grand Challenge Research Forum today. And I'd like to ask Provost Liz Magill to come up and open this forum.
Well, good afternoon, everyone. No, I'm not Mike Lenox. I'm Liz Magill I'm the provost. It's great to see you all on this lovely day. I'm really thrilled to welcome you on the Grand Challenge Forum on Environmental Resilience and Sustainability. It's really exciting to see so many of you here from so many different schools and disciplines across the university. There are many, many, many experts in the areas that we're going to talk about today, far more than we could include in a single forum. We look forward to hearing all ideas and suggestions. This panel is being live broadcast. Did I say that correctly? No, it's being web, whatever it is. People can watch it if they're not in this room. So hello to you who are not in this room. We have intentionally structured today's program to allow for discussion after each panel, so please be prepared to jump in and ask questions, make comments, make suggestions. So it's just not, we won't have just a series of presentations, but we'll, as much as we can in this relatively large group, engage with one another. So having an interactive process, a working group of sorts, along with the panelists. I will say last week's Grand Challenges Forum on Brain and Neuro, we had some really surprising folks, comments from the audience that really energized some of the panels, so raised things they hadn't thought about, so it was a fun conversation. I do have, first and foremost, to offer some thanks. I think everybody who's here knows that planning and executing an event like this takes a lot of work. Hundreds of details, large and small, need to be handled. And I want to first thank Karen McGlathery here in the second row, for those of you who don't know Karen. She is the director of the Environmental Resilience Institute. She's been deeply involved in the planning sessions, gathering faculty feedback last summer in August, organized by ERI. The whole ERI team has worked a lot on this, have been really critical partners and advisors on the topic. Thank you, Karen, for you and ERI's enormous assistance here. I also want to thank the really dedicated staff of Ram's shop, not just Ram himself, the Vice President of Research, Ram Subramanian, but that office has organized these forums and made all of the moving parts move forward. I also want to thank the team of Ram Subramanian and Megan Barnett, who is the Vice Provost for Academic Initiatives in my office. I know all the panelists and many of the faculty members here have worked with them as we got the broad conversation into panels and had those panels focus on what they were going to say today and say to each other and say to the community. So I feel really fortunate to have a collaborative relationship with Ram, which I've had from the beginning, even before the beginning, as well as Megan in my shop, and that they together also have a great relationship. Really talented, very motivated and organized individuals, and really committed to this effort and our research ambitions as a university generally. Most of all, I want to thank the panelists from today. We asked you to do a lot, I know, in a short period of time, and it's been exciting to me to get to hear updates about how you all have worked with each other and what we're going to hear today. I know it's been a lot of work, and you have a lot on your plate, so I'm really, really grateful. Let me step back just a little bit. Jim and I announced last summer that as part of the university's strategic plan, we were committed to making substantial investments in the environmental resilience and sustainability. That's one of the 5 research areas that were staked out in the strategic plan as ones where we wanted UVA to move, in the language of the strategic plan, from prominence to preeminence, or you might just say, really move the needle for UVA and the broader world. We wanted to focus on areas where we could bring together UVA's many different strengths across grounds in STEM, in the social sciences, in the arts and humanities, and in translational and clinical settings to lead in these areas. So we solicited input from across grounds and assembled the panels you're going to see here today, and we gave them a really big assignment come up with 1 or 2 moonshot ideas. I know many people don't like the word moonshot. I might have counted myself among them before I was part of this. It suggests a single goal of getting to the moon. And the challenges we see in the environment and sustainability are really complex. They're very multifaceted, and it's going to require multiple approaches, obviously, and not a single solution like going to the moon. We chose the term moonshot, though, because it captures 2 important things that resonate with me. It's always helpful to say our ambition is incredibly high. We want our ambition to be as high as we can possibly meet, and maybe further than that. And I think it also conveys a level of inspiration. Besides that, there is a popular understanding of the moonshot idea that may not be fully borne out by reality, and I'm going to quote here from John F. Kennedy. In the moonshot speech that he gave to Congress, this is what he said. In a real sense, it will not be one man, I would say person, going to the moon. It will be an entire nation. It is for all of us that we must put in the work to put him there. So that final point for me really captures the spirit of grand challenges. It's not a single researcher, a single discovery, as important as those things are, that are going to solve these challenges, but it will be all of us working together across this great university, thinking about how we can move the needle, how we can change the outcomes in the world for the better, for the benefit of the planet and for humanity. Everyone is in this room, I think, because they share my own passion for the advance of knowledge, for deepening our understanding, and very importantly, for sharing that knowledge with the world. It serves the greater good. I think it is, to get a little sappy about it, it is a noble and it is a very vital endeavor. I hope one thing you take away from today, and I suspect there will be many, is a sense of excitement about the work that is happening right now at this university with incredible people and what's on the horizon for us collectively. I think we're in a distinctive position to advance knowledge in ways that are going to improve the human condition for future generations. At least that's my hope, and I know it's yours. And I can tell you that President Ryan, Ram, the deans of the schools, our faculty, and so many others are dedicated to this goal, and we collectively should think of ourselves as having the highest possible ambition for the future. So thanks for being here today. Thank you for engaging in this collective experiment, the Grand Challenges Forum, something we've not done before, at least in recent memory. I know all of you have brought a collaborative spirit to it, a wisdom, an expertise, and vision as we have this conversation. I'm now going to turn it over to Megan Barnett, our Vice Provost for Academic Initiatives. She's going to introduce the first panel today and go over some of the details. If I'm allowed to say, we have a visitor from the Barnett family who's tuning in from Florida, who might give us notes after this conversation. Megan Barnett's mother. So, my mother's passed away, otherwise I know she'd be watching.
Okay. Actually, I'm Mike Lenox, so I'm just kidding. Thank you all for coming today. As Provost Magill said, the faculty members the panelists have really put in a lot of work and effort, and they've come up with some really exciting ideas. But before we get to the fun part, where we get to hear about that, we just have a couple of logistics. First of all, we are live streaming and recording this event. Secondly, as you all know, we have 3 panels. Each one is going to go for about 45 minutes, and then we'll have about 20 minutes for Q&A and discussion, and we hope everyone will participate. If you do have a comment or a question, just raise your hand and someone will bring you a microphone. Please wait until you have the microphone to start talking, because as Liz mentioned, there are a lot of people, including my mom, watching from home, and we want them to be able to hear what you're saying. And then finally, if you don't get a chance to talk today, we will be taking comments during the event and afterwards on the Grand Challenges website. So please feel free to submit suggestions electronically. You can Google the Vice President for Research website, and there's a Grand Challenges page there. So with that, we'd like to welcome our first panel, which really is moderated by Mike Lenox. It's Climate Mitigation, Removing Carbon Through Technology, Behavior, and Policy. And we have Ellen Bassett, Lisa Colosi-Peterson, Scott Doney, Brent Gunnoe, and Deborah Lawrence. So thank you.
Well, I am Mike Lenox, and it is an absolute pleasure to be with you all. I'm a professor at the Darden School of Business with interests in these areas. And just to remind you again, we are joined by a wonderful panel of leading thinkers here across the university. Ellen Bassett from the School of Architecture in Urban and Environmental Planning. Lisa Colosi-Peterson, who comes to us from the Engineering School, actually my alma mater, in the Engineering Systems and Environment. We have Scott Doney from the Environmental Sciences Department in the College of Arts and Sciences, Brent Gunnoe from the Chemistry Department in the college, and last but certainly not least, Deborah Lawrence out of the Department of Environmental Sciences out of the college as well. Before I turn it over to the panel, I just want to make some opening comments and frame really the challenge that faces us. Because when I think about a grand challenge, I can think of none so grand and so challenging as climate mitigation, our topic today. I think the reason I was asked to moderate this panel is I recently had a book published from Stanford University Press called The Decarbonization Imperative. And the basic challenge that we face when it comes to climate change and climate mitigation is that we need to, in essence, reduce emissions to net zero by 2050, if not sooner. So for those not familiar with these terminology, what does this mean? Well, first of all, the climate scientists tell us that to be able to mitigate the worst impacts of climate change, we need to restrict global warming to 1.5 degrees Celsius preferably, or at the very least, 2 degrees Celsius. And that means that we're working through what we might think of as a carbon budget. As we emit greenhouse gases, we're approaching that tipping point where that will no longer be the threshold that we've hit. So the notion of net zero is very simply that we need to reach a point in time where our net emissions of greenhouse gases are zero or even preferably negative. So what does that mean? Well, of course, we have the emission of greenhouse gases mainly through the burnings of fossil fuels through human activity. Fortunately, there are ways in which greenhouse gases, especially carbon dioxide, are absorbed through various types of carbon sinks, like the growing of forests and the like. But the fact of the matter is, over the last 150 years, we've exceeded that natural capacity of the globe to absorb those emissions. So when we think of net zero, there's two parts of the equation I want you to think about. The first is reducing emissions, reducing those emissions created by human activity. And the second is what we would call carbon capture and sequestration, this idea that we might be able to absorb some of these CO2 emissions and carbon emissions to offset those that are emitted through our activity. So just to put the emission side in perspective, the IPCC reports that we have basically 5 major sectors that are where we call Scope 1 emissions, where the emissions are actually occurring. The first is transportation. Surprising to some, that's only about 1/5 of global emissions. Automobiles, but also more challenging things like airplanes and maritime travel, ships and the like. So you're probably all aware of the electric vehicles that are hitting the roads, and that's wonderful, but we need a lot more if we're going to get to net zero in that sector. Second large sector that you're probably mostly aware of is electrical generation. That's about 1/4 of all global emissions. This is primarily the burning of fossil fuels, in particular coal and natural gas. Fortunately, there's an amazing story that we can tell over the last decade or so in terms of renewables and the price of renewables that have come down over time to the point in many applications renewables are cost competitive with things like natural gas, at least in certain applications. But we still have a very long way to go, and there are a number of important challenges there, including intermittency. The sun doesn't always shine, the wind does not always blow, and that creates some complexity as we think about building out a new grid that has the capacity to have large-scale renewables on them.
The third sector I would mention is buildings. Buildings are about 6% of global emissions. The use of natural gas, for example, to heat your home, or the use of natural gas on your stove. The fortunate thing here is that we have viable technological solutions that are already commercially viable as well. Things like electric heat pumps, things like electric stoves. The challenge in this sector is how do we reformat our built environment, the investments already made in the millions of homes and businesses out there that have adopted fossil fuel technology to switch over now to more renewable sources. And to be clear, a lot of the path forward is about electrification. How do we electrify our buildings? How do we electrify our vehicles, which is going to put even more demand on that electrical grid. Last but not least, I want to mention two sectors that don't get quite as much attention in the popular press. The first is industrials. This is including all forms of manufacturing and mining and the like, but three sectors in particular are particularly problematic: steel, cement, and petrochemicals. All three of those sectors are major greenhouse gas emitters in the actual construction of those materials. Fortunately, there are efforts to try to decarbonize these sources, including things like green cement, but we're a long way away from having those be commercially viable and widely adopted at this point. And last but not least, the sector I personally worry about the most, agriculture. Surprising to many is agriculture is nearly a quarter of global emissions. There's three major sources of these. One is livestock. You do see this in the press sometimes, but cows belching is actually a major greenhouse gas contributor, in particular belching methane. The use of nitrogen-based fertilizers releases nitric oxide, which is a potent greenhouse gas, and in many ways, our whole global agricultural system is very dependent on those fertilizers. And then last but not least, of course, is land use policies. And what we need is to be creating carbon sinks, and we're going to talk quite a bit about that, I imagine, on the panel. The fact of the matter is we're still deforesting our globe, and that's contributing to global warming as well. So again, the scope of the problem is huge. The opportunities for challenges are many. And we're going to hear from the panelists in a second here about some ideas for grand challenges, not only overall, but specific to UVA. But before we do that, I want to go through our panelists and have each of them just briefly share their specific focal area of research and interest. And I'm just going to go right down the line here. So Ellen, do you want to kick us off here, please?
How does this work here? Oh, it's on. Huh. Well, lovely to see everybody here. Thank you very much. My area of expertise is actually that latter part that you just spoke about, which is land use policy and planning. I spend a lot of time thinking about zoning. I did contemplate talking to you about zoning today, but I figured you might flee for the doors. So I'm going to speak from a more broad perspective. I'm going to talk about research in urban planning, which I consider a policy science with a very applied sort of view, as well as our allied disciplines within architecture and landscape architecture. And when you look at the research in those disciplines, we've been primarily focused on mitigating climate change. So this is really how to reduce carbon production through the spatial, through the built environment, and different policy interventions. So I think of this as a stream of research in those fields, which is like what we need to do. In also thinking about today, I thought, gosh, how long have I been thinking about this question about what we need to do? And I realized, depressingly, I did my master's degree over 30 years ago. And so for 30 years now, planning in particular, but also landscape architecture and architecture, has been saying and proving the same things in terms of the research there. We need to conserve land and natural resources, particularly carbon sinks like forests and wetlands. We need to design with nature. A very famous landscape architect talked about that. And think of nature as a form of technology, not as something that humans should just use as they wish. We must build our communities in the most compact ways. We have to stop reliance on the single occupancy vehicle that burns petroleum. We have to design buildings and human settlements that, basically are light in the land and integrate natural systems. So thinking of biophilia and green building sciences. We need to invest in renewable energy, integrate it into the landscape, and this has to be done in a distributed fashion and working across the scale. That has been the consistent message from planning and architecture and landscape for literally 30 years. The most environmentally positive people, this may come as a surprise, but perhaps not, live in New York City, right? They live in small spaces, they consume less, they share heating through the walls with their neighbors, they use transportation, they walk and bike a lot more than we do. The people who are worst from a carbon perspective live like we do in Albemarle County. They live in large houses on big parcels of land, they have fragmented habitat, they've taken down trees, and they drive to work. So I think a lot of us might feel a little bit of guilt in that, but this is definitely the case. So research on this compact development and growth has really shown great benefits for carbon reduction. There's a pretty well-known transportation planner at Utah who calls this growing cooler. Unfortunately, and this will come up later when we discuss the moonshot ideas, and maybe part of my frustration with my field, is a lot of this research and these entreaties to protect the land, protect watersheds, build in a more compact manner, have really fallen on deaf ears, right? So it's maybe odd, but I'm going to cite the Washington Post as a form of research. So the Washington Post had an excellent article in August, and it was entitled Way Off into the Horizon. And it documented the relentless march of urban sprawl and urban growth in America, and it's at the expense of ag land, for sure. So between 2001 and 2019, the built-up landscape of America, so buildings, roads, other infrastructures, other structures, expanded into previously undeveloped areas, adding 14,000 square miles of new development. So this is across the contiguous United States. That is an area over 5 times the size of the state of Delaware. So just to give you an idea of how much we've continued to grow, even knowing about climate change. So I'm going to talk about the social sciences and policy sciences later, but just to say that we are still working on this, and I think the most cutting-edge research in my field, certainly in those of us who think very spatially in our research, is the amazing amount of geo-referenced, geospatialized big data that we have out there. And we have this huge opportunity with our data sciences school, remote sensing, drones, GIS, but now, of course, the cell phone, social media, fixed and mobile sensors. This kind of data is pretty revolutionary for us, and it's the sort of stuff that can perhaps address a lot of the transportation challenge. I know that one of my colleagues, Andrew Monshine, is really on the cutting edge of doing this. This is, again, I think, to think of C's is smart cities research.
Great. Thank you, Alan. Lisa.
Our intro? Or
This is just your
Okay,
intro.
okay.
Yeah.
Hi, everyone.
We're
I'm
gonna
from
get
the
to moonshots later. We're
Okay,
gonna have time for moonshots
I'm
later.
here from the Department of Engineering Systems and Environment. My group does a lot of research using a systems modeling tool called Life Cycle Assessment, or LCA. We use this tool to analyze the environmental impacts of a product, process, or system. What's fun for me is that a lot of this work is collaborative, right? I get to work with groups or people who are thinking about a new technology, and we get to help them anticipate what the economic and environmental performance will be in multiple dimensions, right? How much energy will it use? What will the greenhouse gas impacts be? And so a lot of what I think is really cool about this area is not just thinking about what we could do, but really trying to decide what we should do if we're gonna make progress towards the many goals.
Great. Scott?
So Scott Doney, Environmental Sciences. My background is in natural science and carbon cycle and also biogeochemistry. And I'd say a lot of what I do, but also what my field is doing, is really trying to quantify what happens when we emit carbon to the atmosphere. As Mike mentioned, between fossil fuels and deforestation, it's roughly about 5 tons of CO2 per year for every person on the planet. Obviously, a lot more for us in the US than in other countries. But only about 45% of that carbon stays in the atmosphere. And so there's been an enormous effort over the last couple of decades figuring out the fate of that carbon. How much goes back into the land biosphere? How much goes in the ocean? What's going to happen in the future as climate warms up? Will those carbon sources or other pools of carbon in the natural system be released to the atmosphere? And this is really relevant not just for modeling and projecting for the future, but also for verification efforts. And so if anybody's been following the Glasgow conference over the last 2 weeks, a lot of time at the end was taken up by what's called the stock take. It's basically what are the rules for tracking how different countries or different sectors are performing in terms of decarbonizing or these carbon dioxide removal. And you need this framework of the natural sciences to really track what's actually happening. If we actually take an action, can we see carbon dioxide in the atmosphere slowing down or even reversing?
Great. Thank you. Brent?
Okay. Thanks, Mike. Oh, a little too close. I'm Brent Gunnoe from Department of Chemistry, and I want to start by thanking the organizers for the opportunity to participate. I'm greatly looking forward to today's discussion, and all the discussions leading up to this event have been really quite compelling and informative. I also want to thank Ram and Megan and Cheryl for all the work with the panel in advance of today, and all the other panelists for all the discussions we've had. They've been quite enjoyable. My area of research is focused on catalysis, and particularly my group focuses on molecular homogeneous catalysis. And we are primarily focused on processes that are related to large petrochemical production. So these are chemical reactions that are practiced on the scale of tens of billions of pounds per year that consume substantial amounts of energy just to make the high-value chemicals that society demands and needs. We also have a substantial focus on catalytic processes that would enable the use of renewable energy resources to generate fuels and chemicals. And of course, that'll be a focus of a lot of my comments today.
Great, thank you. Deborah.
Hi, thanks for having me, and I echo Brent. It was really fun getting ready for this panel. Scott's already mentioned a lot of the exciting work that we do. I'm an ecologist. I'm in the environmental sciences department, and my own work I'm a tropical ecologist. My own work has shifted from trying to understand what happens in one place, in one rainforest that is cut, to what happens when you cut all around the world. So my methods have changed from collecting soils and plant tissues to using global climate models. So for me, I think the most exciting work in ecology and climate change has to do with trying to understand the future, as Scott already alluded to many of the most amazing ecosystems on the planet. What's going to happen to the Amazon? Right now, it's a sink, at least for the most part in most years. What if it becomes a source of CO2? It's not just a big giant chunk of carbon, it's one of the most diverse places on the planet. So I'm interested in the fate of our ecosystems going forward. I think it matters because we are going to depend on them, as you'll see, to continue working for us and taking up carbon. So really, are they going to continue functioning the same way? This is a big question. So the tropical forests are one place that I'm very interested in. I think a lot of exciting work is happening. And the boreal zone as well, the tundra, what is that going to melt? If it melts, just in case you didn't know, there's a ton of carbon stuck underneath those peatlands up there, and if it melts, we're really in trouble. So I'm interested in the permanence of these carbon sinks, and I think that's where some very exciting work is going on.
Great, thank you. I think that last comment really highlights some of the interdependency between the emissions reduction side and the carbon sequestration side. But to keep our argument, or at least our discussion, in some structure, I want to start with the emissions reduction side. So Brent, I'm going to turn to you, and what would you see as a potential moonshot for UVA to take in that fairly broad emissions reduction bucket there, if you will?
Okay, thanks, Mike. I do want to begin just by way of introduction of saying that my grandfather is a Baptist preacher, and he would often get up and say he's going to talk for 15 minutes about what he passionately cares about, and then an hour later he'd still be going. So I've been accused of having the same genetics, and so I just point that out because I've written...
You've got like 4 or 5.
I know, that's... I appreciate that, Mike, and remind me in a few minutes if you need to. But I preface my comments by saying I've scripted some of this, written down some notes for your benefit to try to keep me on track. The first important point that I want to make in terms of emissions reduction is that projections by the International Energy Agency indicates that likely by 2040, the global energy demands will be increased compared to current demands by about a third, up to maybe close to 50% more. And using current energy processes and resources, this would represent an enormous increase in CO2 production, even beyond the enormous amount of CO2 that we currently emit. Approximately 37 to 44 extra gigatons of carbon dioxide per year. And that's important because I think it makes a pretty compelling case that effective climate mitigation is likely not possible without dramatic reductions in carbon dioxide emissions. And the case that I want to make today is that one viable approach to significant reductions in carbon dioxide emissions will be enabled by advancements in electrocatalysis. I'll come back and talk in a little bit more detail about what electrocatalysis is in just a moment. But for a moonshot, envision a future where photovoltaics are put in places where there's intense sunlight, Arizona, for example, and that the electricity that's generated will be transmitted to chemical and fuel production plants, and electrolyzers would use that green electricity, solar electricity, to make liquid fuels and valuable chemicals. That process requires electrocatalysts in those electrolyzers to do the chemical reactions that are required to make the liquid fuels and the chemicals. And a primary point here is that this vision in this process would enable the conversion of sunlight, water, and carbon dioxide to liquid fuels and chemicals that we currently make from fossil resources. So there's no change in the products that we make. And that's important because there's no change in the required infrastructure to use these products. And so if this vision can be realized, we can readily implement this vision at scale and apply these products and use these products. But a major limitation to this vision is in the field of electrocatalysis. Simply stated, we need better electrocatalytic materials to make the electrolyzers economically viable, or to make the fuels and the chemicals that we would produce from the electrolyzers economically viable. Current materials that we have for electrocatalysis are fast enough and stable enough, but they're simply too expensive. They cost too much. So we have to find ways to generate electrocatalytic materials that do the same thing, but that they're much cheaper. And I'll return to some of that in just a moment as well. I do want to just make an important note that carbon neutral energy resources and what the options are readily known. Solar energy, wind, hydroelectric, nuclear, biomass. And we can estimate the maximum total potential impact of each of these resources relatively reliably. There's some deviation and some debate about this, but pretty reliably everybody agrees what we can do in maximum with all of these resources. And solar energy is the only carbon neutral energy resource, renewable energy resource, I should say, that can meet even current energy demands, let alone the increased energy demands that are being projected. But solar energy presents substantial challenges. It has to be converted to a storable form, because we don't have sunlight 24 hours a day, and a usable form. And I would make the case that usable forms that are compatible with existing infrastructure are the most viable. And that liquid fuels from carbon dioxide and water and solar electricity provide that opportunity. Electrocatalysts are the key components of electrolyzers. They are the materials that use the electricity that is generated by solar or potentially wind and hydroelectric, other carbon neutral energy sources also, and to convert readily available and inexpensive and environmentally benign resources into chemicals and fuels. So just to return to this vision, one point that I want to be certain to make is I am not advocating for the so-called hydrogen economy. This has been discussed broadly. I don't think it's viable that we're going to make hydrogen on a large scale and then transport that hydrogen and use hydrogen in vehicles, et cetera. Rather, the point that I want to make is if we can enable large-scale solar electricity-driven conversion of water to hydrogen with electrolyzers, that opens up many opportunities for use of that hydrogen that don't necessarily depend on hydrogen as that central element and that central chemical or fuel that we move around. For example, hydrogen can be used to reduce captured carbon dioxide to liquid fuels. This is known scalable technology. Once you have hydrogen and carbon dioxide, you can make methanol, which is a liquid fuel in flex fuel vehicles. You can make diesel fuel. You can make gasoline. These are scalable technologies that have been demonstrated already. And a significant advantage, of course, of these products is that they're compatible with existing infrastructure. There are challenges. Carbon capture is an important challenge that is a key component to this. And I also point out that this is not fantasy. There are pilot plants that do exactly this on a relatively large scale. Mitsui Chemicals has a plant that captures carbon dioxide from ethylene production, chemical process. They generate hydrogen using solar electricity and water splitting, and they make about 100 tons of methanol per year with this process. So on an energy scale, not large, but still been scaled up and demonstrated viable. Also, Johnson Matthey just announced that soon they're going to build a pilot scale plant to make almost 1 million liters of methanol per year with solar electricity. And they hope by the year 2026 to produce over 500 million liters of methanol with solar electricity and carbon capture technologies. That's enough fuel to power about 200,000 vehicles. The other point I want to make about this vision and this strategy is it's not only applicable to fuels production, but chemicals production. And this is important because the chemical industry, including ag products that Mike mentioned as problematic, accounts for approximately 10% of global carbon dioxide production. And there are numerous opportunities to mitigate that with electrocatalytic conversion of water and carbon dioxide. One example, as I already mentioned, is the production of liquid fuels from carbon dioxide and water. But other examples in the chemical side include precursors to plastics. So in scalable technology, methanol, which can come from water and carbon dioxide, can be converted to precursors to plastics. Right now, those processes are incredibly energy intense. Companies take ethane and propane and crack them at about 1,000 degrees Celsius. Enormous energy input and CO2 output to make plastics. And I know there are issues with plastics recycling that need to be solved, and I'll touch on that in just a moment. But I will also make a point that lightweight plastics are an important part to reduced energy consumption because we need to continue to make lightweight vehicles and transportation services, et cetera. And so we need to be able to continue to make those compounds and those plastics, but fossil-free resources. And this vision of taking water and carbon dioxide and solar electricity could enable that on a large scale. I'll also note that green hydrogen from solar electricity would be a huge step in plastics recycling, which has become an enormous issue. If you ask any chemical engineer or chemist to design a process to recycle plastics into their starting constituents, almost all of them would include hydrogen in that process. It's almost impossible to envision a way to do this without hydrogen. But we currently make hydrogen from fossil resources, and we produce vast amounts of CO2 in that process. And that is not environmentally sustainable. In fact, just yesterday I was talking with a chemist from Dow Chemical who makes a lot of the world's plastics, and they have a growing effort to recycle plastics. And I posed the simple question to her, can you envision a future of recycling plastics without green dihydrogen, solar-driven hydrogen production? And she simply stated, likely not possible. So the plastics recycling issue really probably depends on us making hydrogen from non-fossil resources. Mike mentioned the ag industry. Ammonia production, which is a precursor to fertilizer, consumes 2% of global energy demand, and most of that is hydrogen production, which is used to reduce dinitrogen. Again, fossil resources, steam reforming, heat and beat, a lot of energy input. If we can capture solar energy as electricity and drive electrolytic production of hydrogen, you would immediately solve this issue and make fertilizer production sustainable and much more environmentally benign. So there are numerous opportunities.
Point out the time here.
Am I already over?
Yeah.
All right, I'll wrap it up. So the last thing I want to say that we can talk about is that I think the University of Virginia is positioned to make dramatic impacts in this area. There's expertise in electrocatalysis and materials across arts and sciences as well as the School of Engineering. And it's a good thing I had my notes. It would have been much worse.
Thank you, Brent. Let me turn over to Lisa and stay on this theme of carbon reduction here.
Great. So I was planning on following Brent, and Brent, I think you did a really great job laying it out in sort of broad strokes. I was hoping to highlight some of what's already happening at UVA as we balance what's really worth doing versus what we have expertise. Megan mentioned that that was a key part of picking the right moonshot. And so for me, when I think about what's exciting in decarbonization research, I'm looking for at least two things. One, I'm looking for focus on the big sectors, going after the big chunks of emissions. And then two, acknowledging that no single solution will exist, so we're going to have to think about multiple technologies working together in systems, and then applying a lot of data-driven systems approaches to optimizing those technologies as they work together. And so having said this, I'd like to highlight 3 classes of research that are already underway at UVA related to decarbonization, and each of those has those elements, right? Focusing on the big sectors and really including a meaningful systems level component. And so the first sector is transportation, actually focusing on 3 different subsectors within transportation. The easiest subsector to decarbonize, as was said, is personal automobile transport, and UVA actually has really important work in this vein. If we are going to decarbonize via electrification, we need to continue to grow the penetration of renewables in the grid, and we need more reliable, lower cost storage. And so UVA is well poised in both of these areas, a lot of innovation related to wind turbines and mechanical engineering, and then really important work related to storage and chemical engineering. If we move from hard to harder to decarbonize, the next middle area is this heavy-duty freight that Mike alluded to. This, again, for aviation and heavy on-road trucking, historically powered by diesel, but this cannot be decarbonized via electrification, so we need other approaches. And it's exciting to me that UVA has at least 2 collaborative projects in this vein. So the first is an NSF project that thinks about how different kinds of diesel might interact with different kinds of engine combustion modalities and different kinds of technologies. You can see the system, right, the different components. Different kinds of technologies for catalytic converters. Each of those different combinations will give different emissions profiles that will impact the climate and regional air quality in a different way. And so trying to understand where we want to be in that landscape can be valuable. The second project is really related to what Brent said about catalysis, thinking about the power of taking CO2 and turning it into renewable natural gas, again, to supplant diesel. This project is also highly interdisciplinary. So in both of these cases, we're looking at the fusion of chemistry, chemical engineering, material science, and environmental systems modeling, again, to sort of understand what's possible. And then going to the hardest subsector of transportation to decarbonize aviation, as was said, I'm actually part of a team that was tasked by VDOT, the State Department of Transportation, to build a technology roadmap to understand what we could do to make aviation more sustainable in the Commonwealth. That work paved the way for a current project at the specific request of the Secretary of Transportation, really outlining what the supply chain would look like for us to make locally produced sustainable aviation fuels. Again, using some of the chemistry that Brent alluded to, and really ensuring that Dulles stays competitive with airports on the East Coast. And so when I think about transportation writ large, it's really exciting that UVA attacks so many of those dimensions. Also, I think Ellen laid the groundwork for thinking about how transportation is itself really a surrogate for mobility and accessibility. And UVA, as she was saying, has really good strengths in alternative modalities, right? Biking, pedestrian safety, planning, and really working together with VTRC, the research arm of VDOT, which is on our grounds. I think they make a really important partner in all of this. The 2 other sectors that I was going to talk about were buildings and industry. With respect to buildings, I think it's well known that the UVA Link Lab is the home for CPS, Cyber Physical Systems work. Really innovative, really interdisciplinary approaches to making buildings lower energy consuming and less greenhouse gas emitting, really applying all of those smart technologies, really valuable. And then industry, again, as was said, dominated by cement, steel, and petrochemicals. UVA also is really well positioned in this area. Andres is here, he could talk about his green work, his green cement work. We also have some petrochemicals work, thinking about global systems modeling, and then, as Brent said, thinking about how catalysts fit in through all of that. And so when I step back and think about all the sectors, it's exciting to me that UVA has already pockets of strength. And when I think about what makes us distinctive within those pockets of strength is that it's this application of technology plus X, or engineering plus X, where X is this appreciation for systems and how the parts fit together and how to contextualize these decisions that we'll be making with scarce resources in a way that lets us really sort of hopefully maximize benefits and minimize costs.
Thank you for that. It really resonates with me, this idea that we have to think about sectors, but it's the integration and the interdisciplinarity that's inherent in trying to solve those. We've talked a lot about climate reduction. Now let's turn to the other side of the equation, carbon sequestration or carbon removal. Scott, do you want to comment on that, please? You want to hand it over to Deborah first?
Deborah's going first.
We call that a cold call at Darden there. That was good.
Thanks. That was really great to hear the setup with, on the emissions reduction side. So I'd like to have my comments in 2 different pieces. First, the framework, which is what can the land do to mitigate climate change? What can the land do to absorb CO2? And then I will touch on what I think UVA can do to make that happen. So I want to frame this by telling you to please consider with me the global scale, the entire Earth. I'm going to focus on the terrestrial, so the land surface, and Scott can talk about the ocean perhaps. So the total land surface, ecosystems that range from the wild, a wild forest, a vast tundra, grasslands, all the way to an intensely managed agricultural system. So we have a lot of different ecosystems. And so that's our framework, global and varied ecosystems. They all serve us in many ways. So there's kind of 3 buckets for climate. things that we can do as humans that, say, with a cost component included. They are protect, manage, and restore. So protect and manage actually have to do with avoiding emissions. So that's the mitigation side, and I'm not going to talk about that because that's part of it. I'll just give you a little spoiler. It's about 10% of global emissions could be eliminated in a cost-effective framework if we just protected and managed our forests better. But that's not really the part we're talking about today. Right now, I'm going to talk about that third bucket, which is the restore bucket, which is how we actually use these natural ecosystems to take CO2 out of the atmosphere. So not putting them in, but drawing CO2 out. So on a global scale, cost-effective, if you just reforested everything and re-wet all the wetlands, again, where it's cost-effective, you could take care of about 5% of our global emissions today. So 5%. If you did farming better, if we managed our farming and our grazing lands better, improved management, we could add another 5%. Okay, so that's about 10% of our current emissions could be handled by better management of our ecosystems. To get beyond that, we have to think about kind of technifying agriculture. So this gets back over that way. You know, and also thinking about the land and its connection to the energy sector. So what am I talking about? There's these two other big pots of emissions, of CO2 sequestration potential. And I think of them as the slow burn and the fast burn. The slow burn is something called biochar. And the fast burn is bioenergy with, biomass energy with carbon capture and sequestration, which is BECCS. So there's biochar and BECCS. Biochar, the idea here is that you slowly burn organic residues, could be from agricultural waste, forestry waste, municipal waste. You have some organic matter, you burn it slowly, you create a stable carbon, and you go and sprinkle that carbon on the land in agriculture, and it becomes part of the soil. That's really low tech. It creates, both of these systems use these organic wastes, produce some energy, and end up with carbon in the soil. But they're very different. So biochar is this low-tech, slow burn, low temperature system. It goes into agriculture. BECCS, biomass energy with carbon capture and sequestration, is high-tech. It uses high temperatures. You burn this organic matter at a high temperature, you generate much more energy. You have to use technology to transform that CO2 that's produced by burning organic matter into something that can be transported and stored, and you end up storing that CO2 somewhere else in a geologic formation in a specific place. No benefits to agriculture, but certainly benefits us because we've controlled the climate. So biochar and BECCS, like slow burn, fast burn, both of them are technologies. They're doing things in a different way. They both put carbon dioxide into the ground. Together, they can deliver probably another 10%. That's a lot. So that thing, we don't know how to do that very well yet. The other stuff, managing agriculture well, putting trees out in farms and forests, we know how to do that. So that's not a place where we have a lot of work to do. This BECCS and biochar, that is work that needs more to be done. So I think that if I was talking about a moonshot, I would say that the real moonshot here is actually managing the land beautifully so that we stop degrading our ecosystems and start enhancing them. So that's kind of a rosy way of putting this very simple goal of trying to figure out how to manage our ecosystems so that they absorb carbon instead of continuing to lose carbon. What can UVA do in this area? Clearly, there's a bunch of ecology to do. We are not a bunch of agricultural people, but there's plenty of basic ecology that needs to be done. It's partly around the idea that these are not, we don't know if they're permanent stores of carbon. If we're going to plant forests, there are risks. Fire, drought, pests, diseases, all these things are likely to occur more as the climate changes. So if we're going to invest in putting work into nature's climate solutions to growing trees or restoring our soils, we need to be sure that's permanent. So there's some ecology to do to understand, mostly modeling, trying to anticipate what the future climate will do to our ecosystems. There's also Earth system science that would say, what happens if we ecologically engineer the entire planet and we do all sorts of things to the Earth's surface? What if we put forests everywhere? What are the consequences for the flows of water that we need? What are the consequences for our local climate, regional climate, global climate? The feedbacks. We want to know. We want to anticipate what happens when we do this ecological type of engineering. And then finally, in the environmental sciences, and probably in other fields, we heavily invest in remote sensing. So can we use remote sensing to measure and monitor our progress? We don't want to have to go out and look at all these trees by hand, right? We want to be able to look from space to see if the forests that we are planting are healthy and taking up the carbon we expect. Again, this also touches on some of the governance issues. And that gets me to the other part. So there's clearly ecology and earth system science to do with how you get carbon dioxide through photosynthesis into the soil or into plants. But there's so much more that we do at UVA. So what about this? The economics of risk, when you have this potential volatility in this natural carbon sequestration with fire, how do you deal with that risk? That's perhaps an economic question. What about the ethics of land use? Who is it who owns land? Who is it who can plant the trees and benefit from that new carbon market? Who is displaced when trees replace farms? What about the sociology of rural communities? All of this is going to happen not in towns and not in New York City. This is going to happen out there in the hinterlands. So what about the sociology of rural communities? How do they work? What is the role of religion, values, culture? What about the anthropology of farmers? Who are they? How are we going to convince them either to take up entirely new techniques or return to some techniques of the past that they've given up? What about behavioral economics? If we can figure out what to do, how do we nudge farmers into doing it? And what about the role of law and public policy in codifying and institutionalizing whatever it is we figure out that those farmers respond to? We need that in the law. So I think there's a role for really the entire university to participate in figuring out how to help the land do all it can to give us a better climate future. I think we have lots of strength across the disciplines, and it's not all in the sciences.
Deborah, we're going to make you a social scientist one of these days.
I am one, actually.
Oh, that's good. I agree. Scott, maybe there's another part of the world that Deborah wasn't talking about, maybe the oceans?
Going back to Mike's introduction about net zero, the models that were being used, being run real time last week in Glasgow, were primarily dependent upon BECCS, this bioenergy with carbon capture and sequestration, and afforestation. And the policy scenarios that are being played out to get to net zero really do require massive industrial scale carbon removal from the atmosphere. So, I had said that right now for each person it's about 5 tons of CO2. The models suggest that we need 2 or 3 tons per person of removal in addition to decarbonization because some of these systems are rather recalcitrant. And so some of the new technologies, some of which are being done at UVA and some of which tie into some of the things that Brent and Lisa were talking about are, if you like, a little more technological. Both Brent and Lisa talked about what you would say is reuse of CO2, capturing CO2 and then reusing it as fuel. As Deborah mentioned, a lot of these models assume the ability to sequester this carbon in geologic reservoirs. And so that's a geologic problem, but it's also an engineering problem of how to get the carbon, where to put it, and then tracking it over time. And then other approaches are things like accelerated weathering. On really long time scales, excess carbon dioxide in the atmosphere will be removed because basically rock weathering. But can we accelerate that? So in addition to biochar that can be added to soils, people have talked about grinding up rock and adding that to fields or grinding up rock and putting it in the ocean. And then at the very far sort of technological extreme is what's called direct air capture. It's physically, chemically capturing CO2 out of the atmosphere, not out of the flue gas of a power plant, but actually out of the atmosphere, and then sequestering that in some geologic reservoir. And, you know, Brent had mentioned some scales of pilot projects. The biggest direct air capture pilot project right now that's on the books, if it works, would be about 4,000 tons of CO2 per year. So that's about 800 people's worth of annual emissions. And so there is, for all of these technologies, a vast scaling where if done at small scale, it looks benign. But as we scale it to larger and larger levels, for example, if you deploy BECCS, models suggest that because of the economics of land use, that a lot of that BECCS will end up in the global south, which raises not just local equity issues, but global environmental equity and justice issues. And so I'm going to sort of follow up on Lisa and a little blend of Lisa and Deborah in that I think UVA's strength is really looking at this as an entire system. So the engineering, the natural science, but also the social science, the legal perspective, the business perspective. You know, none of these technologies is going to do more than a pie slice. You know, if a technology can do 5% or 10%, that would be spectacular. But what are the geophysical or engineering limits? What are the social limits for social license and acceptance? What are the environmental impacts are that going to be? What are the social impacts of that are going to be? And I really see that we can bring together, you know, for me, the moonshot would be picking one or two of these approaches, whether it's land-based or technological-based, and really look at it from end to end. You know, how can this scale from a life cycle analysis? Does it actually remove carbon from the atmosphere in net? Because we know, for example, a lot of land-based systems, if you implement it in one place, all that does, for example, is push timber harvest to another location. And so can we show that it removes carbon in net? That if we're going to take carbon out of the atmosphere, is it stored someplace that's permanent and durable, or is it just vulnerable to re-release in a few years? A lot of the carbon offsets that people have paid for when you fly on an airplane have been planting trees. A lot of those were in Northern California, and they burned this summer. And this goes to the insurance and risk industry of, you know, how do you make a business case for this if carbon removal is then vulnerable to carbon release? So I really see this, and I'll then hand it over to Ellen, as an opportunity for us to be the leader, not just in a particular technology or not just in a particular place, but the place that somebody would come. I really want to see this from a whole human perspective, from the engineering all the way to what does this do to people and how do we govern it and how do we run this in a business case, because most of the plans involve some amount of market incentives or market economy. I'll turn it over to you, Ellen.
Thanks. Well, I'm supposed to bring in the social sciences, but since you have all done such a great job of articulating it, I almost feel like what I'm going to say is going to be repetitive. I don't have a moonshot idea. I actually say, or have thought throughout this whole process for preparing for this, that the moonshot ideas that have been put forth by my colleagues are actually all very exciting. You know, I am a red-blooded American, right? I believe in technological process and American can-do and all that sort of stuff that we've been brought up thinking about. You know, I was reflecting on the fact that I watched The $6 Million Man when I was a kid, you know. If anyone knows that show, you look it up if you don't know the reference. Okay, so I'm going to just talk a little bit more about the social sciences, act a little bit like a Cassandra, although you will believe what I'm saying, I'm sure. And I want to point out that the paths to addressing global climate change over the last 20 years have really been stymied. They've been politicized, and they've frankly been rejected by the people who really need to embrace them the most, right, which is human beings. And I think it's really a tragedy. I think we all probably are sort of cognizant of climate grief and the tragedy that we're feeling around climate change. You know, we're taking down so many species with us, and we're in fact inflicting costs on communities. So I did a lot of work in Africa, who, you know, have played very little role in sort of bringing this about. So I really appreciate the emphases on social equity, thinking about the global south, thinking about what the impact of these technologies might be. So to make the moonshots real is just what has been said here already. We have to address the social, political, economic, and cultural side of carbon reduction and removal. We have to address, you know, this by integrating the humanities and the social sciences, law and the policy sciences into this research and not have it be a mere afterthought. And I mean, I love working with these people because they don't relegate it to a mere afterthought, and I think that's really fantastic. I'm just gonna pick on nature-based solutions for a minute, which is kind of unfair because Deborah is so acutely aware of this. It's really tempting, you know, I study land, I think about land a lot. I think about land tenure and land ownership. It's really tempting to reduce the shift that we might be able to make in land to being just a matter of price. You know, we'll put a price on carbon and voila, things will change. But we all know that land is a lot more than dirt, right? Land has extraordinary meaning in American society and in other societies as well. Land is highly personal and emotional. So if you go talk to a farmer who has a centennial farm, you're gonna learn about his or her relationship with the land. Land, of course, is a marker of community belonging and you know, being. So in Africa, one of the worst things that can befall you is to lose your land, is to become landless. Land has incredible connections to wealth building and to power. We know that, the landed gentry. Land is intimately linked to democracy, so we'll get to the democracy one next. Thinking about, you know, voting rights, we're certainly linked to land ownership. Jefferson's yeoman farmer being, you know, part of the stability of the new American Republic. And we also know that land has a spiritual dimension. So I'm thinking about the EPT students who are reading John Muir, and he's on the top of some crazy tree in you know, Yosemite in a lightning storm, very close to God. So when landowners reject wind farms or solar panels, you know, large-scale reforestation, they're questioning BECs and things like that. We really shouldn't deride them as irrational or unable to understand their own self-interest. We have to understand their embedded decision-making, right? We have to understand what it motivates for people to make change. I went back in sort of prefacing this and looked at the grand challenges discussion that took place in August, and so I'm going to call out a few people who had great ideas. Michael Allen of Religious Studies, I don't think we've ever met. He framed it really well. He put out that we have 3 gaps that we have to work on: the knowledge action gap, the science action gap, and the values behavior gap. Len Chopa emphasized the need to really think about how do we accelerate adoption of these technologies and these ways of living. And he highlighted the problem of partisanship, right, in governance over climate change. And then Jonathan Colmer talked about the need to invest in science communication. And I think we're all acutely aware of how the science around climate change and carbon has been so politicized and has created great obstacles to moving forward. We have great strengths across the university to address all of these things. I think in A&S, I think of politics, of course, media studies, psychology, just to name a few of the departments. We have incredibly strong business schools that think about these sort of things. Our law faculty clearly is thinking about the institutional framework. And just to call out the A school, you know, we think a lot about designing landscapes. We think about equitable community participation in design. So we have really great strengths that I think we could integrate into any of the moonshots that have been discussed here. And I don't want to forget Batten, because, you know, this emphasis on public policy and leadership is unusual for a public policy school. And I find it ironic but rather inspiring that the best person leading us in climate right now is a teenager, right? And she's out there speaking truth to power. And what I really want are leaders who have power to actually speak the truth. So that's my bid for the social sciences, humanities, and others to be involved in this moonshot.
That's a great quote there at the end, Elena. Can I steal that?
Go right ahead.
Okay, that's wonderful. We're running a little short on time, so let's open it up now to any questions you have for the panelists here. I believe we're going to go around with microphones. Is that correct? So just raise your hand if you have a question or a thought you want to share with the panel. There we go.
Hi. Is this on?
Oh, yeah.
So the question I have for UVA is, you know, it's an important thing that we could address. It's just the ethics of population increase and population decrease. It seems like if there was less people on the planet, there would be, you know, less CO2 emissions and the like. And, you know, UVA has plenty of grad that can handle that problem, but it's not something that's in the public discussion. Is that not really a moral imperative? You know, how many people is enough on the planet? And, you know, do we sacrifice every other organism on the planet to just unstopped human growth? So that's not something that you see discussed a lot. And I think that might be worth UVA looking into. There's one other more technical thing I'd like to point out is that what about nuclear energy? We shut down the engineering department, the nuclear engineering department, but yet, you know, thorium reactors, breeder reactors, there's probably 2,000 years of energy production from such a thing, gives no global emissions. That's within our grasp. But no one's too happy about the idea of breeder reactors because of the nuclear proliferation risk. But on the other hand, are we just, you know, sacrificing the future generations because we're too afraid right now? It seems unworthy. So I think that's another thing that could go into the conversation. Anyways, two ideas.
So there are two things, let me just repeat. So the first was, I'm curious everyone wants to tackle this one, population growth, and should we be doing and studying and coming up with solutions to maybe control population growth? And then let's ask that one first. Anyone want to try to tackle that one? Deborah? Oh, sorry.
I was just going to say that there is the Project Drawdown. It has a great book of the top 100 solutions, and one of the top solutions is educating girls and women. So that's in there. People are thinking about it, and it's a really tried and true method. So there's not a lot of mystery about how to slow population growth. So I'd say, yes, it's out there. I also would just push back that, I don't know, population is not the only thing. It's our use of energy, and it's the source of that energy. So those people out there right now don't use a lot of energy. They want to, and they deserve to. So we need to figure out how to get clean energy to everybody, and let's just go hard on the educating girls. That's what I would say.
And then I'll just follow up. I mean, this has been talked about, but I think I don't think it's the right way to be thinking about it. There's a huge disparity in energy use and CO2 use across the planet. And I think there's a moral imperative, particularly in the global south, where economic level is very closely, at their stage of development, very closely linked to energy supply. And so I think there's a moral imperative for the developed world to reduce our energy consumption and our CO2 emission, and to provide the resources, both capital and knowledge and engineering, for the global south so that they can raise their energy use on a per capita basis and improve their economy.
The second question related to nuclear power and its role in all of this. I don't know if someone wants to discuss that.
I'm going to sidestep that question, leaving aside the sort of normative discussion about whether or not societally we should be embracing nuclear, but I think that logistically or practically, it would be hard for UVA to really achieve prominence in that area, especially, as you said, we ended the nuclear engineering program, and so it may be a good approach for someone. I'm just not convinced that we would be that institution.
Note on nuclear power, I think that the potential advantage, of course, is that it's viable, it's scalable, we know this. It brings a whole host of other potential issues when we scale it. But I'm just assuming that the politics of scaling nuclear energy are even more complicated than everything else we're talking about. And I think it's just probably the ship has sailed on that, in my opinion.
Yeah, just to put a couple of facts on the table, there's one new nuclear plant under construction in the United States right now. France and Japan, who are leaders in nuclear technology and nuclear adoption, are actually scaling back their nuclear for, in Japan's case, obvious reasons. And so at least the market is speaking at this point that it doesn't seem to be a big piece of the solution. Not to say that if the politics change, the NIMBY problems are resolved, it could be part of it. Another question.
Identify yourself, please.
Sure. Hi, I'm Andres Clarence. I'm a professor in engineering systems and environment. I want to thank the panelists. That was really terrific. I thought that speaking as an engineering professor, I thought that Ellen's points about the importance of the social sciences in solving these problems were really critical. There was an opinion piece in Science last week saying that science needs a new lane, and it was written very much from the perspective of the health sciences and talking about COVID and all of the innovation that the medical fields did, and yet there was just this huge gap between the innovation that occurred over the past year and then people's willingness to adopt these interventions. And so the piece really speaks to the need for science to think more creatively about how we implement the technologies and the innovations that we're making. And it seems to me, I think the ideas that were put out today in terms of grand challenges on the mitigation space are terrific. But I think one place where UVA has excellence from the outside is in the social sciences. And, from my experience, a lot of times with projects, engineers will come to social scientists and say, can you evaluate the economics of this? Or can you evaluate the sociology of this after the fact? And it seems like we need a new way to do it that from the get-go, from the inception of the projects, that's going to lead to better outcomes, better adoption, better implementation of the moonshots, whatever they end up being. It's a comment, not a question, but if anybody wants to answer, they can.
If you don't mind, I'd actually like to speak to that one too. And I think, as an economist who cares about public policy, who teaches in a business school, really think about the systems integration pieces here. And you can't think of them independently. As an economist, when it comes to something like livestock, I might say, let's put a tax on cows. Could you imagine the political rancor in the United States of trying to pass a cow tax? And so to separate out the political legal from the economic or the behavioral or the just general societal is not productive. And we need to be thinking about these as an integrative fashion, along with the technology and the science, of course. Scott, did you want to jump in on that one? Okay, great. Let's see, we have time for a couple more questions.
Oh, hi there.
Hi. Can we start here?
Okay, hi there. Two quick questions. My name is Kat McHugh. I'm with the Office for Sustainability here at UVA. Question one is, there was a couple weeks ago, I think there was a Washington Post article about how the nations at the summit had pretty much underreported their emissions. It was, I didn't do a deep dive into the data, I just read the story, and it was very disconcerting, to say the least. So any comment on that? And then the second piece was, I think, Deborah, when you were talking, it just occurred to me that all of these moonshots and ideas and research, I mean, this takes time to bring all of these things together. And I'm just curious if anybody wants to say how this affects you sort of personally as leaders in these fields to try to be catching up with your research with a system and an issue that is constantly getting worse, it seems?
So did everyone hear that? So I think the first question was about misreporting or underreporting by countries.
I can do that. So that was Juliet Eilpern and colleagues wrote a piece in the Washington Post. And they had looked at all of the, so at Glasgow, the policy mechanism is NDCs, nationally determined contributions to trying to decarbonize. And one of the problems is what goes into those, what are the rules? Scientists like to or engineers like to look in fluxes and mass and things like that, but it's what do you actually count? And the problem which they found, working with a group called the Global Carbon Project, is that a lot of countries had counted some of these natural sinks that Deborah mentioned earlier, that forests are regrowing naturally already. Forests are taking up more carbon because there's more CO2 in the atmosphere. And unfortunately, when we frame this at the beginning, net zero needs net zero human emissions. There's no way to stabilize climate unless human emissions stop, because natural sinks need to continue to remove carbon dioxide. And this is where the sort of political wrangling where countries want to count these natural sinks is not, it's actually, it's leading us down the road because it's not going to get us to net zero. But yeah, it was an excellent piece, and it was, I think, actually a really good example of how investigative journalism worked well with the scientific community because they used the science databases that said human emissions are here, the UN's coming up with here, what's the gap and why, and identifying that.
The US does that. We count our natural sinks.
Canada does it.
It's not just some little country in the South.
The second question was almost more of how do we deal with the overwhelming nature of this problem? I will say, as someone who just recently wrote a book on this, I'm asked this repeatedly about, can we really pull this off? And my response on my darker days is there's no way. But then I am an optimist by nature, and so I kind of constantly come back to we've got to get moving on this. And I think the scientists on the panel will probably confirm this, that God forbid we don't achieve the goals for 1.5 or 2 degrees, we still have to keep working at this. Like, we don't want to go to 3 degrees, 4 degrees. Like, we have to address this problem. I don't know if anybody wants to comment on that. Let's do another question in the back there.
Great, thank you. I'm Matt Reidenbach. I'm from the faculty in the Environmental Sciences Department. I really like the conversation here about sort of the main issues that we're really facing. And I think about like the university and the role of the university and the good that a university provides. It's really sort of training the next generation students to go in the future. And could you, I'd like to hear just some comments about, are we training our students effectively in tackling these issues? Should we change the pedagogy or how we're doing obviously this knowledge transfer to the next generation?
And may I reframe the question slightly, which is, what role does teaching and education play in a moonshot? Bring us back to our moonshot point here.
Oh, I'll try.
It's critical.
Well, first of all, I think we would all admit that at least our graduate students do half or more of the work, so probably more. So we know that our students are actually engaged deeply in the research enterprise. Are you talking about undergrads, Matt, or are you talking about everybody? All of us?
Yeah.
Yeah. I think we've already seen, at least I've seen, that graduate students want more than their narrow education. They seem to want it, and they seem to be trying to get it in whatever way they can. So I think they would like to learn more than just whatever piece of the pie they're supposed to work on. And maybe interdisciplinary teams is a way to do that.
Could I add one thing? Related to graduate students, I actually think that is what would contribute to a talented student picking UVA engineering versus our peer institutions, this desire for meaningful cross-training and individualized mentorship. And so it was asked, like, how do you manage working on an ever-moving target? And how do you do that quickly? When I think about ways that the university could spend money, it worries me that hiring is a very long game, right? Finding the people, bringing them in, attending to DEI, all the things that we have to do to hire well. In reality, the grad students do the work, and if you want me to work on something new with someone who has a completely different set of incentives that I do, I need a grad student to do that for me. And so I actually think that they are the ones who want this interesting cross-training. I also think that they are best positioned to work on projects now, even if the projects have something of a moving target. And to Matt, I don't know if you were asking about undergrads, but I teach Introduction to Engineering. I have 80 first years every year, and I have my little song and dance, and I say, if I had my way, no one could graduate from UVA without confidently and succinctly articulating the greenhouse principle. These are engineers. It's some of the hardest, criteria to get into the school. And I say, who needs 5 minutes to check with Google or a partner to confidently and succinctly articulate the greenhouse principle? And almost all of them want a chance to refresh. And so I don't know. I think some of them hear what we're saying and are really valuable partners. We've got interns on UVA sustainability. But I think that if we're asking, are the masses getting minimum exposure to the urgency of the problem, I think the answer is no.
Yeah, I'd just like to emphasize thinking about the totality of education and broader perspectives, and especially in science and engineering, that being able to engage in collaborations is absolutely critical to providing that type of education. So students in my group, for example, they get expertise in catalysis, and they think every single day about turnovers and longevity and lifetimes and stability, et cetera. But very often students will get asked questions that are broader than that, and they're not pushed on a day-to-day basis to think about this. But when you're in collaborations that are large and multidisciplinary, they receive those questions, and it prompts them to think about the context of their research in ways that they would not ordinarily do. And just a really simple example, if we were to collaborate with Lisa's group on a new electrocatalyst, she would come to the group and say, well, you're trying to make this. here's what you need in order to make hydrogen at $2 per kilogram. And those are the types of things we never think about. And she would bring into the perspective of, well, the capital investment in an electrolyzer is 1/3 of the cost of the electrolyzer, and 80% of that is because you're buying platinum. If you put iron in and you have this efficiency, you need this much iron, and these things are really important to have a total education. And you get that from multidisciplinary efforts.
Time for one more question.
Yeah, Osman Özbulut from Engineering Systems and Environment Department. So we talk about the BECCS, the bioenergy with carbon capture and storage, but the carbon value of the biomass can exceed or may exceed the energy value. So I think there is a growing interest in the use of the biomass for carbon removal and storage. So the term that they use is the Biochars, so biomass for carbon removal and storage. And I think UVA is well positioned for that type of research as well, as there are advancements in materials technologies and manufacturing, and this the biomass can be used in long-lived products such as the building materials without converting them into energy. So I just want to add this.
Those relating to biomass, I don't know if any of you want to have any follow-up to that?
I think the comment was related to thinking about building materials as a carbon lock, right, for permanent sequestration. And actually, that was a line in my talk, but it got cut because I thought Mike was going to cut me off at 5 minutes. But actually, it occurs to me that thinking about locally produced bio-based building materials as a long-term carbon sink, right, really actually threads some of what was said, right? Thinking about ways that we could allocate land for production of different things, and then trying, hopefully, to be local about how we create resources that we then use, and then knowing for sure that those stocks would stay permanent, hopefully not burning down.
So we have time, I think, for one last comment from each panelist, and I want to do this rapid fire, and they didn't know I was going to ask this, but I just was thought from Lisa's comments just a little while ago. We're trying to think about grand challenges here and opportunities for moonshots. We've talked a lot about different topics along those lines. I want to talk about how we do it, and in particular, the interdisciplinarity that we all seem to recognize is needed here. So obviously, part of the motivation here is funds. If you have a certain amount of funds, how do you encourage interdisciplinarity towards these different moonshots that we've identified? And I'm going to start, since I went this way last time. Deborah, you get to go first.
Great.
Everybody else is having more time
They get to
about.
think for another 2 minutes or one.
Everybody has like 30 seconds. This is rapid
I'm with
fire.
Lisa. The graduate students that is the engine of this university. If you didn't know that, you should. So I say giant, giant opportunities for graduate students.
Great. Brent?
Yeah, well, I would have to agree with that, and, thanks, Deborah. And money brings people together in ways that other things don't. So, funding these collaborations, at least the seeds to get things started to bring people together is the strategy that has to be implemented.
Great. Scott?
I'd say, we're a pretty low wall between departments and schools, but I think there's still a lot of opportunities. And, ERI has been really good at that on some of these topics already, on coasts and water. And I think we need, in addition to bringing in students, we just need ways to free up faculty so that they can spend time working with faculty from other places across the university.
Great. Lisa?
Those are mine, right? Paying the grad students to buy time, right? So that we can not have to write grants to do this intersectional work.
Great.
So I have a slightly different perspective because I'm in a professional school. So we don't have so many students who are doing deep research over a lot of years, right? They're with us a couple years, they may be participating in projects, but those are the practitioners, those are the professionals who are going out in the world and actually building the buildings, interacting with communities, advising the firms, whatever. So we have to really think of a way for the research function to also have a translation into action. What does it mean for you when you are in the world as a UVA grad who wants to affect change through your profession? And that's a little bit of a different twist than what was talked about with others.
And as someone at a business school, I would concur with that, and the interest amongst our students for these issues and these challenges and being on the solution side is very high. Let me just end by thanking our panelists once again. I also want to thank Megan and Ram for their leadership here from the Provost office and from the VPR's office here. Very excited about where this might lead in terms of the university and the grand challenges that we're trying to identify. So let's give a round of applause to our panelists, please.